You ever just look at a video game or a website and wonder, how in the world does a bunch of text turn into that? It really feels like magic, doesn't it? But it all starts with a plan. Today, we're going to follow that exact path, right from the abstract blueprint of code all the way to the incredible spectacle you see on your screen. All right, so here's our game plan. We're going to start with the basics, the language of code itself. Then, we'll get our hands dirty building with C. After that, we'll level up to some smarter tools with objects. Then, the fun part, how code actually gets onto your screen. And we'll wrap it all up with the mind-bending math that creates entire 3D worlds. Okay, let's jump right in. You wouldn't build a house without architectural plans, right? Well, the same goes for programming. It all starts with a core idea, a philosophy. So that's where we're going to begin, with the big picture concepts that guide how all code is written. So, this first big idea is called a programming paradigm. And the best way to think about it is, it's like a style of architecture. Are you building something minimalist and clean, or something complex and ornate, like a Gothic cathedral? That choice, that paradigm, sets the rules for everything else you're about to build. So here we have two of those major styles. On one side, you've got procedural. This is like a recipe. You do step 1, then step 2, then step 3. It's a straight line of instructions. Simple, right? But on the other side, you've got object-oriented. This is completely different. It's less like a recipe and more like building with Legos. You create a bunch of self-contained little objects, like a wheel, an engine, a steering wheel, and then you make them work together to build a car. Okay, so we've got the architectural plans. Now it's time to grab our tools and start building. And we're going to start with a classic, the C programming language. This is one of the originals, the foundation for so much, and it gives us the absolute basic nuts and bolts we need. You can't build anything without materials, and in C, these are your basic ingredients. You've got your int for whole numbers, like 1, 2, 3. Float for numbers with decimal points, like 3.14. Char for just a single letter. But then, you have pointers, and these are really interesting. A pointer doesn't hold the data itself, it holds the location of the data in memory. It's like having a treasure map instead of the treasure itself. So here's something you gotta understand. The code that we write, the computer has no idea what to do with it. It speaks a totally different language. So it has to go through this whole translation process. What we write, our source code, gets pre-processed. Then a compiler steps in and translates it into a language the machine can understand. Only then does it become a program you can actually run. It's a whole assembly line just to get from our ideas to something the computer can execute. Okay, so following a simple recipe is fine for baking a cake. But what if you're trying to build, I don't know, a space station? You need more sophisticated tools. You need a way to manage all that complexity. And that's exactly why we have object-oriented programming, or OOP, and languages like C++. The whole concept of OOP really boils down to one key idea, the class. And the class is super simple to understand. It's not the thing, it's the blueprint for the thing. The best analogy? A cookie cutter. The cookie cutter defines the shape, a star, a gingerbread man, but it isn't the cookie itself. Right, so if the class is the cookie cutter, then what's the object? Well, it's the cookie. It's the actual thing you create from the blueprint. And what's cool is you can take that one cookie cutter, that one class, and create as many individual objects, as many cookies, as you want. And this is why OOP is such a game changer. It has like 3 superpowers. First up is inheritance. Say you make a blueprint for a generic vehicle. You can then create a car blueprint that inherits everything from vehicle, but adds its own stuff, like 4 wheels. Then there's encapsulation. This is just a fancy word for keeping things tidy. It bundles all the data and the functions for a specific object together in one neat little package. And finally, my favorite, polymorphism. This sounds complicated, but it's not. It just means you can tell different objects to do the same thing, and they'll do it their own way. You can tell a dog to speak and it barks, but tell a cat to speak and it meows. Same command, different results. Super powerful stuff. Okay, we've talked about blueprints and tools. Now let's get to the payoff. How does all this abstract code actually create the websites and games we interact with every day? We're moving from the code to the canvas. This is where it all starts to get visual. Just think about pretty much any website you visit. The basic structure, the skeleton, that's HTML. It lays out where the headings and paragraphs go. But all the cool stuff, the animations, the buttons that do things, the dynamic parts that make it feel alive, that's all handled by scripting languages layered right on top. So the code figures out what to show you, but how does it actually appear on your monitor?
Well, almost every screen you use today uses something called a raster scan. Just imagine a super fast paintbrush starting at the top left corner of your screen and just painting every single pixel, one row at a time, from top to bottom, over and over again, faster than you can blink. The old way, random scan, was totally different. It was more like an Etch-a-Sketch, drawing the image with specific lines instead of filling in the whole screen.
And this is what's so wild to me. You could be looking at the most mind-blowingly realistic character in a video game, right? But deep down, at the most basic level, it's all just a massive collection of super simple instructions. Draw a line from point A to point B. Fill this little triangle with the color blue. That's it. Everything we see is built from these tiny, simple brushstrokes. All right, this brings us to the grand finale. This is the real magic trick. How do we take all those simple lines and shapes and create a totally convincing three-dimensional world on a screen that's completely flat?
I mean, that is the question in 3D graphics, isn't it? You've got this massive virtual world with actual depth to it, and you have to somehow project it onto a 2D piece of glass. How do you do that without it looking, well, flat? Turns out the answer is just a whole lot of really clever math.
And that clever math has a name, the 3D viewing pipeline. It's basically a digital factory assembly line. Here's how it works. Step 1, an artist builds a 3D model. Step 2, the code transforms it, moves it, spins it around, puts it where it needs to be. Step 3 is the real magic, projection. This is where math flattens that 3D scene into a 2D picture, like taking a photograph. But to be efficient, the computer then clips out anything you can't see, anything outside the camera's view. And finally, it rasterizes it, which is just a fancy way of saying it converts that 2D picture into the millions of tiny pixels that light up your screen.
But what makes it all look so real? Well, there are a few key ingredients. First, every 3D object is actually made up of thousands of tiny, flat shapes, usually triangles, that form its skin. For all the smooth curves, like on a person's face or a car's body, code uses some very cool math to smooth everything out. But the real secret sauce? The lighting. The computer calculates the physics of how light would bounce off every single surface, creating perfect shadows and highlights. That's what really tricks our brain into seeing depth.
So there you have it. We went from a single, simple idea to a massive, light-filled world. Code is literally the invisible architecture of our modern lives. It's a language, it's a toolbox, and it's absolutely an art form. The screen is the canvas, the code is the paint, and it really makes you wonder, what are we going to create next?